but I can already start to save some time. So hello, everybody. Without Ned's intro, I'm not entirely sure how much context everybody has, but remote attestation is being standardized in the IETF, the Internet Engineering Task Force. I am a member of that RATS working group. RATS acronym is a little bit tongue breaker. It's Remote Attestation Procedures. Can rather all the little the characters from that. And also we'll talk a little bit of quorum, a cornerstone where everything kind of like runs together. So next slide, please. You can see on the right side the architecture. Oh, that's the intermediate. Yeah, that's architecture first. Next slide, please. You can see on the right side that there's a verifier in the middle of a diagram. This is literally figure 1 of RFC 9334. And this is the diagram that took like 5 years to settle down, to what it says, to simplify, to get too complex, to minimalistic maybe. And the real goal here is that to enable, and there's a context menu, well, thank you, enable a relying party to put some trust in the trustworthiness of a remote peer, here in this diagram, the attester. So the relying party is basically, could in some scenarios be a client, the attester could be a server, can be anything else. It's just the relying party has to understand that 2 things are addressed here, and these are solved by generating evidence. You can see coming evidence out of the attester box and going to the verifier, which we will return to later. This evidence solves 2 important problems. It solves a lying endpoint problem. It's called, this, I want to say, old school attestation guys from TCG also like the lying endpoint problem. It's important that the attester does everything that you wanted to do and nothing else. And that's, it can't lie to you and can't misuse its power as a service in regard to the reliance party's dependency on the service. Also, evidence helps you to understand if it is fresh. So freshness is discussed in RFC 9334 a lot, where this diagram lives. There's all the diagrams. That's basically what come here in the RATS architecture. And freshness means that the assertion that is in the evidence, called a claim, or a claim set, is actually still reflecting reality. So as soon as the evidence message might leave the attester, the attester might change. And while the verifier is crunching and trying to get a result if this is a good or bad state, an intentional state or some other unwanted state, it might already change. So it's really about the composition of the attester. And to create that evidence, to base that trust into trustworthiness somehow, attesters need roots of trust. You otherwise do not have a starting point to create a chain of trust of assertions where to begin with. And a root of trust, you just trust, that's in the term. And it's typically in an isolated environment that is hardware isolated, embedded secure elements. TPMs are good examples. CEs are now very much the thing, and thereby the SCV-TDX trust zone world comes into this. All these can become certain roots of trust by trusting code that runs in them blindly to create the first measurement about the health, about the trustworthiness of a attester. And then, well, all this is done to basically cater the relying party. And there's so many different services, so many different platforms and compositions out there that my cell phone would not be able to understand them all. So the burden of appraisal of that evidence is offloaded to a trusted third party that's in the middle here, and that is called the verifier. So this is the core layout and goals. Next slide, please. There are 2 very popular patterns. These are also specified in RFC 9334, the RATS architecture. I'm just quickly repeating them here. For example, when the relying party comes on, it just expects an attestation result. So this means that the attester already has that kind of ready or is creating it on being triggered by the relying party by sending its evidence to the verifier. It personally knows. And the relying party doesn't have to talk to the verifier. That's an interesting way to look at it. It's called a passport model, where I get the passport from my country. My country is my verifier, and it takes a long of vetting first time, like, you know, eye color and all the evidence, the claims that define me. And then when I finally have my passport, it's my attestation result, I can show it around at every customs service desk in the world. and there's easy information about me. So that's why this is called a passport model, talking directly to the attester. I get some evidence to a verifier. That is called doing a background check model. You get all this stuff, and then have no verifier how to process it. There is breaking. Is it only me? Oh yeah, that is not good. Is my voice okay? Okay.
It's coming
Hopefully
back now, so I think it's better, Henk.
Okay. Yeah. Well, sorry. I hope it will just stay the way. No, it's wobbling at times. Let's see if this works. Moving on. Next slide. So this root of trust basically is where the turtles all the way down. So as reference, you can see the turtle on the right. Terminates with the bottom turtle, which is the root of trust. That is, for small devices, good enough. You can have a element in your component in your attester that you blindly trust, and that is endorsed typically by having a public key that you can associate with a trust anchor, and you trust that trust anchor. So that can be staged. You can, with this root of trust, measure the next layer. In this example, also from RFC 934, a testing environment, root of trust in my example, checks the bootloader. And if that turns out to be okay, you can increase your trusted computing base from the root of trust to the bootloader. Now that is your blob you trust. And now that, for example, could check via remote attestation procedures a next layer, that is the kernel. And if that turns out to be fine, it can become part of your TCB. And so as long as these selection trees are not too big, the measurements are relatively small. So it is typically a goal to keep this layered set as small as possible, because you probably will result in a deterministic measurement each boot cycle, the smaller the TCB is, and thereby the cheaper the cost and the complexity. The larger your TCB becomes, so for example, if you include user space, it might make it in a combinatorial explosion of measurements, because today there's threaded systems, there's racing conditions. Sometimes the first measurement arrives before the other, and you're using certain evidence creation mechanisms like a TPM and try to extend a PCR. You might be aware that these will come up with different quotes. You have to replay the logs, and it is a lot of data. The evidence becomes very large, and you start to get complex verifiers because to take into account a lot of composition possibilities. So while a small root of trust or a small TCB is fine, sometimes you just need a bigger one. But I think in general, to keep this goal, smaller TCB is better. And a transparent TCB is best if you can see all that code. Maybe not from the root of trust by design, because you trust it blindly and the vendor basically that is creating it. But every other code that is measured after that, in best case scenario, is also transparent, like open source. And you could pin a commit to these things and on GitHub, whatever, and you can really check on your create a local verifier. You can build a whole system and check trustworthiness. That is the best case scenario. But I think also there are a lot of models where this is not as transparent as I just highlighted. Next slide, please. So that's basically the goal and the core of the remote attestation architecture. Again, we're missing NAT's context a little bit, but I hope that is not a huge problem. The verifier from the diagram has not only evidence as the input. Of course, you need something to compare the evidence with, and you need something else. And so let's maybe move on a slide so we can have a look. Yeah, we have the diagram again. Evidence is coming in. That already elaborated on. Attestation results, easy, small, digestible, hopefully only 2 formats, and that's it. So like not the heterogeneity of the evidence Wild West, where you have a gazillion, so maybe a lot, hundreds of evidence formats potentially. So you need to understand this evidence inputs, at least an reference value provider that gives you for all the claims that are collected on the attester to assess the trustworthiness to be checked. These are called sometimes reference values or well-known values or golden measurements. Lots of synonyms for this. They're all doing the same thing. You compare them. And then some things the attester can't say about itself. For example, that it is very tightly secured, like the CARA HSM is a 19-inch computer thing that is very, very protected. And if that thing becomes an attester, it can't really tell as a computer system that it has good physical protection and a good case and an alarm system around it. So these are endorsements, for example. There can be other endorsements that are based on some reference values. For example, sometimes the attester is not really good at identifying itself. And then you get some measurements. And as a vendor, you know, if you get these 5 claims that are measurements, I know it's this version or it's this type of device. This is then endorsed based on the reference values that you successfully checked. And so there are sometimes conditional endorsements. So in the end, it's basically reference values, so things that the attester can say about itself, and endorsements that the attester. And those are then processed via appraiser. We have a quorum processor on the right side. Basically, what I told you, you check the reference values with the evidence claims all the time, add endorsements when appropriate, at least at the very beginning. If they're just neutral, you can immediately identify the attester, for example, by its signing key and its corresponding public key. So you add stuff via key identification or sometimes via reference values and add more endorsements. And this is then the appraisal's claim set. You build up an internal state via these inputs from quorum. And then policy kicks in all the time. So this appraisal claim set is also fueled by decisions that are relevant to assessing trustworthiness. Sometimes a firmware version was revoked, for example, because it was like faulty and buggy and maybe even initially modified on a global scale, and thereby you don't want that anymore. So there's policy. Sometimes they can tell you that there can be an updated input of endorsement and reference values, the quorum file, which we come to in the next slide. They can tell you that. But in the end, the policy helps you to do all this appraisal. It's not just indications of quorum. Quorum only has a very limited amount of capability to tell you how these reference endorsement values should be used. And this is on the next slide, please. Where the quorum file is basically a bundle mechanism. RIM, by the way, I'm not entirely sure if this is well known, so I didn't write it out. Is a reference integrity manifest. I think it was in the title of this subsection. So while you can see that reference does not really include endorsement, we realized that during working with this, that an endorsed value is typically coming from the same area of stakeholders and authorities, like reference values. Sometimes a vendor, sometimes an external party that evaluated them, that certified them, like FIPS or CC or something. There are multiple sources, and these can publish quorums about an attester. So you have to match these components in an attester with certain identifiers, and thereby a quorum is composed of commits, module identifiers. And these module identifiers in the end include reference values, endorsed values, and the attestation keys. I was highlighting you can identify via keys often. That is an interesting fact. So these are the main contents. It's a little bit abstracted. There's more complexity here, but it's broken down of a commit. So a quorum is a bundle of commits. And these are the claims that you require by a verifier to do the appraisal. Next slide, please. So to get a little bit more specific from the abstract, this is a little CDDL, concise data definition language for JSON and or CBOR. And we have a reference triple record here. That is the very basic thing of associating a reference value, which is in the measurement map, with an environment, which is basically identifying claims about the component. And you can see here on the right, the environment is populated with 3 claims. It's a UUID or an ID specific by the vendor. It is a vendor name and a model name. And the co-RIM publisher deemed this commit content, this reference triple record in the commit, enough to identify a certain environment in that component. And there's a single measurement associated with that hopefully comes via the evidence. So if you find these three claims, you can understand which component is in the attester. And if you also retrieve, associate with that, this one claim in evidence here at the bottom, this X, then you can say that this environment obviously matches that reference thing and put that as successfully appraised to the attested, to the accepted claim set. That is a general procedure. It's pretty simple. co-RIM tries to be agnostic of the evidence, so it has a relatively separate format. Why we have this triple thing. Triple, it is not linked data. It is similar to it, but it doesn't provide you with context. It's just really the triple, which is a reference triple record, is basically the predicate which combines environment, the subject, with the object that is the measurements, the reference measurements. Yeah. So that is why calling this a triple, because it's again this subject predicate object thing, which is a general concept called a triple, but we are not doing linked data. Please do not be confused by the term triple here. And that way, we are still sometimes reconsidering calling it a triple, but semantically, it simply is. So this is how reference values are associated with environments. This is how the endorser and the reference value provider creates co-RIMs and explaining the attester to verifiers to do the appraisal. Next slide, please. So here we can see a more complex one. This I already highlighting, or I already highlighted, that sometimes you need a few reference values in order to proceed. So here is a conditional endorsement that needs certain conditions set to associate endorsed values in the end. And so these endorsed values cannot be known by the attester itself. They come from the endorser. And the condition basically, not super surprising, looks very similar to the first thing that we saw here on the last slide. There were measurements are associated with an environment, but this is now a condition. If these certain things are in the ACS already appraised, then you can add the measurements from the endorsed triple record. These can now be processed in the same way as evidence. So if you would look at the RETS endorsement internet draft, in the which I haven't put as unfortunately did not put as a reference here, you would see this two sides of a coin, and evidence and endorsements are on one side of the coin, and the reference values are on the other side of the coin, because evidence and endorsements both tell you something about the attester, and reference values are always about the appraisal procedure. So in this case, you're reusing the measurement map to tell you something about the attester. And on the left side, where it is a state for environment record, it is used as a reference value, actually, where you appraise something about the attester to understand if it's really the thing. So this is why we reuse the same structure as a condition. So basically, it's all about code reuse, because it's a concise reference integrity manifest. We want to keep the code small and the verify mostly simple. So next slide, please. Yeah, and this is basically, sorry. This is basically a summary of what I just told you today. We want to cater relying parties with attestation results. Attestation results must be easily digestible. You cannot expose the complexity of the attester and just tell all of that. Sometimes it's actually confidential, or privacy considerations are like red alert. If you expose all that evidence, you need the trusted third party to filter that. Often you need multiple of these verifiers, because not every verifier shall know all. That is like the separating confidentiality for privacy, for example, or just because vendors have their own verifiers. But all that, in the end, is aggregated in an accepted claim set that ultimately is fueled by policy, which are today out of scope of the RETS Charter. And you use existing policy language to fuel them. I can give one example of the validation project, which is the OPA Rego language, which is also used by Microsoft Azure, for example. So that's simple there. And all these relying parties get easily digestible and hopefully uniform EAT sized, I want to say, people will tell you what that is later, attestation results. So, and this is all to take care of the Wild West ecosystem that is the tons of different evidence formats, which all are fine, hopefully converge at some point, but we can't wait for that. We are trying to consolidate the verified design, the input format quorum, and the output format attestation results in a general strategy, I want to say, even not only in the IETF, but also the global platform in TCG. And this is it. Thank you.
Thank you very much, Henk. I will take just one or two questions if there are any, either online or here. If you're online, please use the reactions. Just a question. I don't see any in the chat. I see lots of people clapping. We're all clapping here as well. Thank you very much, Henk.